In this video, we will have a look at rational number and their decimal expansion. Since we know the fact that a rational number exists in the form of p by q, where the denominator or q cannot be 0. The decimal expansion of a rational number can be determined by checking the prime factorization of the denominator or q. If the prime factorization of q or the denominator is of the form 2 to the power n 5 to the power m, where n and m are non-negative integers, that means n and m will be positive integers. So whenever we have q in the form of 2 to the power n 5 to the power m, that is q can be expressed in terms of 2 or 5 or both only, then p by q will have a terminating decimal expansion. That means the division will stop or terminate. Now if the prime factorization of q is not of the form 2 to the power n 5 to the power m, that is we get some other integers other than 2 and 5, where n and m are again non-negative integers, then p by q will have a non-terminating but a repeating or recurring decimal expansion. So just by checking the prime factorization of q, we can determine whether a rational number will have a terminating or a non-terminating repeating recurring decimal expansion without actually dividing. Now for a note, in case of a terminating decimal expansion, where q is expressed in the form of 2 to the power n 5 to the power m, n and m being the non-negative integers, the greater of the two between n and m, whichever is greater of n or m, determines or indicates the number of places after which the decimal expansion will terminate. For example, if we have q in the form of 2 to the power 2 5 to the power 3, so 3 being the greater number indicates the decimal expansion will terminate after 3 decimal places. Now let's check some question in order to understand this properly. Now without actually performing the long division, we'll state whether the given rational numbers will have a terminating decimal expansion or a non-terminating decimal expansion. For terminating decimal expansion, we will also represent the decimal expansion. The first question is 17 by 250. Here the denominator or q is 250. So on prime factorizing 250, we'll get 2 into 5 into 5 into 5. 2 into 125 is 250. 5 25s are 125. 5 5s are 25 and 5 1s are 5. So we have our denominator or q 250 as 2 into 5 into 5 into 5. That is 2 to the power 1 into 5 to the power 3. So it is in the form of 2 to the power n 5 to the power m. So we can say that this particular rational number will have a terminating decimal expansion. Since 250 can be expressed in the form of 2 to the power n 5 to the power m, 17 by 250 will have a terminating decimal expansion. Now checking the power, 2 to the power n 5 to the power 3, between 1 and 3, 3 is the greater number. So we can also figure out that decimal expansion will terminate after 3 decimal places. Now let's find the decimal expansion as well, and without actually performing the division. Now in order to get the decimal expansion without performing the actual division, we need to have equal number of 2's and 5's in the denominator. Here we have 3 5's and 1 2. That means we have 2 2's less in the denominator. Now in order to make it equal, what we need to do is the 2 2's which are less, we will multiply in the denominator, and in order to maintain the equality, we need to do the same in the numerator as well. Now next we'll have 17 into 2 square, or 2 2's are 4, by, now in the denominator we have 2 to the power 1 and 2 to the power 2. So adding the exponents, 1 plus 2 will again be 3. So we have both 2 and 5 raised to the power 3. Multiplying 17 and 4, 4 sevens are 28, 4 ones are 4 plus 2 will give us 6. 68 by 2 fives are 10 raised to the power 3. So we have 68 by 10 to the power 3 means 1000. Since we have 3 zeros in the denominator, we can write 68 by 1000 as 0.0. We'll put extra 0 because we have only 2 digits here. 68. So this is our decimal expansion of 17 by 250. Now the next question, 11 by 3125. 3125 can be expressed as 5 into 5 into 5 into 5 into 5. So 5 fives. So 3125 equals to 5 into 5 into 5 into 5 into 5, or 2 to the power 0, 5 to the power 5. It's also possible that sometimes we don't get either 2 or 5. In such cases, we'll list the power or exponent as 0. In this case, it's 2 to the power 0 into 5 to the power 5. Since 3125 exists in the form 2 to the power n, 5 to the power m, so 11 by 3125 will have a terminating decimal expansion. Since out of 0 and 5, 5 definitely is the greater number. So the decimal expansion will terminate after 5 decimal places. Let's check the decimal expansion as well. 11 by 3125 can be expressed as 11 by 2 to the power 0 into 5 to the power 5. Here we have 5 fives and 0 twos. That means in order to make equal number of 2's and 5's in the denominator, we need 5 2's in the denominator. So 2 to the power 5, and we'll do the same thing in the numerator as well. Now simplifying this, we'll get 11 into 2 to the power 5 will be 32, 2 to the 4, 4 to the 8, 8 to the 16, and 16 to the 32 by, now we have both 2 and 5 raised to power 5. 11 into 32, multiplying 11 and 32 will get 352 by 2 5s are 10 to the power 5. Now 352 by 10 to the power 5, we will have 1 and then 5 zeros. So now on dividing 352 by 1 lakh, we will have 0.00. Since we have 5 zeros but only 3 digits, so 2 zeros we'll put in front, and then we'll write 352. So the decimal expansion has terminated after 5 decimal places. The next question, 77 by 210. Here the numerator and denominator can be reduced further. Both of them are divisible by 7, so let's reduce it. 7 11 is 77, 7 3 is 21, 7 0 is 0. So 77 by 210 can be expressed as 11 by 30. Now let's prime factorize 30. So on prime factorizing 30, we'll get 2 into 5 into 3. 2 15s are 30, 5 3s are 15, 3 1s are 3. So here we do have 2 and 5, but apart from 2 and 5, we also have another number which is 3. So this indicates that 30 is not in the form of 2 to the power n, 5 to the power m. It also has some other digit. Since 30 does not exist in the form 2 to the power n, 5 to the power m, so 77 by 210 or 11 by 30 will have a non-terminating decimal expansion. Next up we have 15 by 1600. This is also further reducible as both numerator and denominator can be cancelled by 5. 5 3s are 15, 5 3s are 15, 1 carried over, so 10, 5 2s are 10, 5 zeros are 0. So 15 by 1600 can also be expressed as 3 by 320. Now let's prime factorize the denominator, which is 320. The prime factorization of 320 will give us 2 into 2 into 2 into 2 into 2 into 2 into 5. 6 2's and 1 5. Since 320 exists in the form of 2 to the power n, 5 to the power n, 2 to the power 6, 5 to the power 1. So 15 by 1600 or 3 by 320 will have a terminating decimal expansion. Since 6 is greater of 1 and 6, so decimal expansion will terminate after 6 decimal places. Let's check the decimal expansion as well. 15 by 1600 equals to 3 by 320 equals to 3 by 2 to the power 6 into 5 to the power 1. Here we have 6 2's and 1 5. In order to make equal number of 2's and 5's in the denominator, we need to multiply 5 to the power 5 in the denominator. In order to maintain the equality, we need to do the same thing in the numerator as well. This is how we find the decimal expansion without doing the actual division. So now we'll get 3 into 5 to the power 5 will give us 3125. 5 5s are 25, 25 5s are 125, 125 5s are 625, and 625 5s are 3125. And in the denominator we have both 2 and 5 raised to the power 6. Multiplying 3 into 3 1 2 5, 3 5s are 15, 1 carried over, 3 to the 6 plus 1 7, 3 1s are 3, and 3 3s are 9 by 2 5s are 10 to the power 6, which can also be expressed as 9375 by 1 and followed by 6 zeros. So 9375 divided by 10 lakh. Since there are 6 zeros, so decimal expansion will have 6 digits after decimal places. Since we only have 4 here, so we'll have 0.2 zeros followed by the digits that we had in the numerator. 0.009375 will be the decimal expansion. Sometimes the question may also come in this form where the denominator or q is already prime factorized. Here the denominator is 2 to the power 3, 5 to the power 2. That is, q exists in the form of 2 to the power m, 5 to the power n. So 23 by 2 to the power 3, 5 to the power 2 will have terminating decimal expansion. Out of 3 and 2, 3 is definitely the bigger number. So decimal expansion will terminate after 3 decimal places. Let's check the decimal expansion as well. Here we have 3 2's and 2 5's. Number of 5 is 1 less than number of 2. So in order to have equal number of 2's and 5's in the denominator, we'll multiply 5 to the power 1 in both numerator and denominator. Multiplying 23 into 5, we'll get 5 3's are 15, 5 2's are 10, with carried over 1 we'll have 115 divided by 2 into 5 both raised to power 3. 115 by 10 to the power 3, or 115 by 1 followed by 3 zeros. We'll get 0.115. So this is our decimal expansion of 23 by 2 to the power 3, 5 to the power 2. Now one more example. Here we have 129 divided by 2 to the power 2, 5 to the power 7, 7 to the power 5. Apart from 2 and 5, we also have 7. So q does not exist in the form of 2 to the power n, 5 to the power m. So 129 by 2 to the power 2, 5 to the power 7, 7 to the power 5 will have a non-terminating repeating decimal expansion.